Well, thanks very much, Tim and Jasper, for inviting me to this really fun event. Good to see everybody again. And so this is what I've chosen to talk about. Roughly spans a period of time of 1970 when I arrived as a postdoc at Toronto to work with Phil and Ernie and Don McRae, and continued in the follow-up with the Galactic Radio Patrol to find out if there were other Cygnus X-3s and other transient phenomena, up until 1988 when the telescope at Green Bank collapsed on us, right? So that's the span of time, and let's get started. So thanks to Google Earth, I get nice pictures of different places. So here's Burton Tower at the University of Toronto, where I arrived in 1970 as a postdoc with Ernie, Phil, and Don McRae. And I'd come fresh from a PhD at Jodrell Bank, where I'd gone, assuming I would be using these large dishes. You know, that's the reason you go to Jodrell Bank. But I chose a supervisor, Graham Smith, now Sir Francis Graham Smith, who enticed me into doing a radio astronomy project on the first all-British satellite, Ariel 3. And it had a very lofty goal of using the ionosphere as a lens in order to achieve high-resolution imaging at these very long wavelengths. Well, as it transpired, I worked on the satellite for 2.5 years, and then it got launched. And but as soon as it launched, it was clear that our experiment was suffering interference from the Birmingham University electron density experiment. And this was coming through a plasma coupling as a result of being in the ionosphere. It's not something we could have really found on the ground. But serendipity stepped in, and I managed to do a space physics project. I ended up discovering Cherenkov radio emission from incoming auroral electrons, of all things. So on arriving back in Toronto, I was now faced with the opportunity of actually doing ground-based radio astronomy. So I went with Phil to Green Bank, Ernie to ARO, and even that madman Alan Yan. I participated in one of his VLBI experiments. And I got very valuable training in the first year, basically, of doing ground-based radio astronomy, which I'd gone to Jodrell Bank to do, but never ended up doing. And but all this good training, on the back of my mind, it was clear if I ever wanted to get a faculty position, I had to show some leadership and initiate some new research program. So the opportunity arose when the Uhuru X-ray satellite was launched in 1970, and they came out with the first all-sky catalog of X-ray sources, albeit not with very good positions. But that left opportunities for radio astronomers, right? And so without much difficulty, I persuaded Phil and Ernie that this would be quite an exciting program to start. And we decided to also add in some peculiar stars. So we'd study the radio properties of newly discovered X-ray sources and peculiar stars. So in my second observing session on this program, which was in September of 1972, a very important occasion in my life, we had planned a multi-observatory campaign. So ARO, NRAO would do the radio astronomy, that is the Green Bank interferometer at NRAO, and then the David Dunlop Observatory, Tom Bolton would man and do spectroscopy on that site, and then we had the DAO in Victoria. And we planned a campaign on the interesting binary star Algol, which had exhibited radio emission and quite variable radio emission. So basically at ARO, I was the sole representative from Toronto at the time, and Mel Viner and Dave Rotelick came up from Queen's. So we were splitting the time with Queen's University. And so, but when Algol was not up, we divided that time so that we could individually do our own projects. And so on the night of September 2nd, I was busily trying to, look for radio emission from some of these peculiar stars and X-ray sources, and we had this terrible, rainstorm came up, and at 2.8 centimeters, the atmosphere is always pretty transparent, but when you get heavy rain clouds, there's some absorption, and that gives rise then to emission, of thermal emission, and that means your chart recorder is going all over the place. And so you lose stability. And I remember thinking, well, maybe we should quit for the day. And the telescope operator was, every 5 minutes, was saying, I think we should quit, you know. And I was thinking, well, in the previous observing run in July, earlier that year, I'd seen Cygnus X-3 go up to half a Jansky. We called them flux units in those days. And so I thought, well, it's just possible under these conditions I would see half a Jansky. So we'd have this one last shot. So we moved the telescope over to Cygnus X-3, and let's see what happened. So here we are. Time is increasing up here, and you can see this ratty baseline. That's all due to the bad weather. And here we are moving on to Cygnus X-3, and the chart recorder goes bang, and it's grinding away. I'm thinking, what's happening there? That's not weather. And then 20 seconds later, which is the nod time, it came back on scale. So I started, you know, you can see me turning down the gain here. And the way we were observing is we had two beams, and we first of all put the beam on the source, one beam on the source, the other would be our reference beam. And then 20 seconds later, we'd move the beam so that the other beam was on the source. So we'd expect to get a square wave. And normally, if you're looking at a weak radio mission, you don't see anything on the chart. It's just a quick look. And you have to wait for 20 minutes, half an hour for the computer to spit out, did you detect anything? But of course, with Cygnus X-3, this was a different matter. And you can see this beautiful square wave emerging here. So at this stage, what's going on? You know, this is not possible. But of course, Cygnus A, the brightest radio source in the sky, is only a couple of degrees away. So obviously, operators turn to Cygnus A. So we took the telescope off Cygnus X-3, we checked the coordinates, went back onto Cygnus X-3, and boom, there it was again. So I didn't know what to think, but you know, astronomers always wonder whether they're going to be the ones that will discover the next supernova. And we'd never seen a supernova go off in the era of radio astronomy, so we didn't know exactly what to expect. At any rate, I quickly got on the phone to Bob Gelming, who was observing. Of course, we were all set up to do Algol, and they were doing the same thing at Green Bank. And he said, wow, okay, I'll call you back. And so about half an hour later, he called me back, and he had the two wavelengths of 3.7 and 11 centimeters, and both of them were showing Cygnus X-3 still going up. And he also reported back that 2 days prior, they'd observed Cygnus X-3, and it was at a level 1,000 times less, 1,000 or 2,000 times less. So this was, you know, made it even more special. And so we spent quite a bit of time on the phone deciding, you know, well, what is this thing, right? And well, we originally, you know, looking at the Uhuru catalog because there's the exciting possibility that these theoretical entities, black holes, would be out there in binary systems accreting material and producing wonderful events. So that was one of the possibilities. But the spectrum was still was much brighter at 2.8 than 3.7 than at 11. So it was definitely a thermal-like spectrum. So we thought, man, well, it could be either in that case. But we're going to assume it's a supernova going off, and we need to alert everybody. So I put out an IU circular right away, and Bob put out another IU circular confirming it's not sufficient that a Canadian find it, has to be found by an American as well. And then we started calling around. And so my first call was to the David Dunlop Observatory. And Sidney Vandenberg was observing at that time. And there's low-lying fog, so the telescope, the dome was closed. But he said, well, I'll go up onto the catwalk and I'll have a look. And so Sidney's one of these rare astronomers that actually knows the night sky fairly accurately. And he went up and looked at Cygnus, and he was above the fog, and he reported, no, nothing happening there. So same kind of result from DAO, nothing of importance. And I remember calling through to the Hale Observatory and thinking I'd get through to a telescope operator, but instead Martin Schmidt picked up the phone and, and he went and had a look too, and again the report was negative. So, you know, astronomers around the world were picking up on this event. They were picking on it first hand through the circular, second hand, third hand, fourth hand. And so before long, every major observatory, no matter what wavelength, was looking at Cygnus X-3. I don't think there's been anything prior to that that was observed as intensively for about 2 weeks, solidly, until Cygnus X-3, as you'll see, decayed away. And one Cambridge radio astronomer was reported to have said, "Thank God it shut up. Now we can do some real astronomy." So, as you can imagine, at ARO, the telex was just going nonstop with reports from, you know, observatories, Jodrell Bank, all parts of the world were reporting in, and I was getting phone calls left, right, and center. And the same thing was happening at NRAO, so we got on the phone. I got on the phone to Bob, and I said, "Look, we need to pull all these, you know, measurements together in one place. I'm going to get in touch with the editors of Nature and see if they're interested." And I did, and they said, not only we're interested, we'll prepare a special issue of Nature Physical Science dedicated solely to Cygnus X-3, which is what they did. So let me show you what some of the results look like. So here's the first big outburst, still the biggest at 23 Jansky. You can see the top are 10.5 gigahertz, that's ARO. Then below that, 8.1 gigahertz. And then another ARO at 6.6. That should be 4.6 gigahertz. Beg your pardon. And then 2.7 gigahertz NRAO, and then the Westerbork data at 1.4 gigahertz. And you can see that it clearly was brightest, and even at 1.4, you can see a big delay in the peak. Jodrell Bank came in at 408, and the delay there was truly 5 days. But you can see also that shortly after the peak, the spectrum started to turn over, and it became very non-thermal. It became optically thin, non-thermal radiation. But still, this could be a supernova remnant, right? But if it was, you would certainly expect that things would be hopping in the X-ray. And it turned out to be kind of a non-event in the X-ray. I'm not sure what the next slide is. Yes, here it is, the X-ray. So here at the top, it worked out well. The satellite was, in fact, observing this region, so they had continuous coverage through this event. And you can see that it was just, there's the radio flare up at the top, the timing of the radio flare, and there's nothing really much happening in the X-ray. So that seemed to put a real damper on the idea it's a supernova going off. But they also looked more carefully at some of their previous data, and they found that there was a nice 4.8-hour period in the data, which was then arguing strongly that this was some kind of binary system. So just after Cygnus X-3 decided to shut up, it came back to life again. And so here you see at ARO 3 more flares at 10.5 gigahertz. Incidentally, my wife was 8.5 months pregnant at this stage, and I was calling her, telling her, "Okay, I'll be home soon, but you've got to realize what's going on here." And she's a scientist as well, and so she perfectly well understood. And she probably could have had the baby and all without me, but certainly she would have. But it was good form that I got back in time. So here's a whole bunch of other observations at other wavelengths that were taken throughout this series. And within this period of time, the Meudon Observatory came through with the first 21 centimeter absorption measurements. which indicated that Cygnus X-3 was right out on the edge of the galaxy. There might have been a little bit more hydrogen apparent in the emission line, but subsequent observations with the VLA during October 1982 by John Dickey showed that with the much higher resolution, all you could say is that Cygnus X-3 was beyond 9 kiloparsecs. There was really no clear indication that there was any more galactic stuff beyond that. Okay. So let's move on here. And so here's where the discovery paper was published in this issue of Nature, which has the Cambridge 5-kilometer radio telescope on it. So there was our discovery paper and then Jelming and Balak's follow-up confirmation paper. And then here in the next is the special issue of Nature, which you can see there's a whole list of sources. You'll probably recognize many of the players. And the lead paper in this was our interpretation paper. Basically, on the weekend of the 16th and 17th of September, we'd invited the Queen's astronomers to come to UBC, to University of Toronto, and Bob Jelming came up from NRAO, and we closeted ourselves, and basically we're playing around with van der Laan models and doing calculations, and eventually we're able to come up with a very coherent story in terms of an expanding relativistic plasma with an embedded magnetic field. And we're sufficiently we were lucky to be able to actually calculate the strength of the magnetic field based on this type of a model. And it turned out to be about somewhere between 20 and 60 times the Earth's magnetic field strength. All right, so here's what appeared in the University of Toronto Bulletin. This is showing our observing team with Phil there on the left and myself and Ernie Sequist, all looking a little bit younger. This was my artist sketch. That's me, the artist, sketching this model of an expanding relativistic plasma. And in the paper, we also calculated that the expansion rate could be something of the order of a third the velocity of light. But we didn't actually, weren't brave enough to suggest these were jets. Although in the back of my mind, well, what were the other highly variable radio sources? And by that time, we were aware of jets. But we didn't know about microquasars or anything like that, right? This was to become one of the very first of those. Here's an observation in 1974 where we caught another outburst, only this time Ernie and I were on the three-element interferometer at Green Bank, and we got very high degrees of polarization, up to 14%. Here you can see plots of the degree of the ratio of the degree of polarization of 2.6 to 808 megahertz. So you can see the thing depolarizing as the event transpired. And you can also see the Faraday rotation, differential Faraday rotation. You can see it jumping around, indicating that there was clearly evolution in the depolarization screen within the source as this material either expanded or moved through. Well, here are some of the highlights for Cygnus X-3. Many have followed on subsequently. Discovery of the infrared 4.8-hour periodicity. Also the discovery of UHE gamma rays from Cygnus X-3. They have also found this 4.8-hour periodicity. Evidence of the jet-like emission by Geldzahler. Then in 1985, the claim of a 12.6 millisecond TeV gamma ray pulsar, which was seen on 2 occasions. And we don't have any obvious reason to doubt it, but it's not always seen. But then Cygnus X-3 is one of these bizarre transient things. And you have to bear in mind that the the phasing with regard to this 4.8-hour period is all important. So as you'll see in a moment, one of the most bizarre discoveries was there's these two experiments deep in mines, one in Minnesota and one under the Mont Blanc, that were doing experiments on proton decay. And these guys have nothing to do most of the time except to trace down, try and correlate the background muons with whatever. And somehow they hit upon trying to correlate with the position of transiting of Cygnus X-3. And they found that there was a significant correlation with the transit of Cygnus X-3 and a significant correlation with the phase in the 4.8-hour period. It's not just one group, it's two groups have both found that, right? And so the really interesting thing is that they are not able to account for this by assuming that the primaries are gamma rays. There are not enough gamma rays to produce the muons that they see down below. So they have proposed that there is a new neutral hadron which is produced by Cygnus X-3, the universe's biggest cosmic accelerator that we know about in our galaxy. So there's this interesting signet or neutral hadron that perhaps is yet to be found. Well, I've got to move on. So let's just show you one of the more recent VLBA measurements of the jet from Cygnus X-3. It's a one-sided jet. We know that the inferred velocity is greater than 0.8 times the speed of light. And we know that the inclination is about less than 14 degrees to the sky, to our direction. And the cone angle is about less than 12 degrees with a period longer than 60 days, which has led one author to speculate that this thing periodically zaps the Earth and could well have evolutionary effects that we have yet to investigate and understand. Okay, this was the famous infrared observations, which proved that the primary was a Wolf-Rayet star with a mass of about 7 to 50 solar masses. Wolf-Rayet stars have blown off their hydrogen envelope, and they have these violent winds. And so based on the 12.67 millisecond pulsar period, we think this is a Wolf-Rayet star with a neutron star orbiting it. Well, as you can imagine, there was a huge press outpouring on this. We had camera crews from Japan, Germany, England, India. They were all up at ARO, all pestering us whilst we were trying to make these observations. And then when I got back to Toronto, I did numerous interviews. My favorite was with Peter Zosky on the morning show. He and I hit it off very well, and so he invited me back, and I got to give 8 20-minute talks on astronomy on his show, which was a really enjoyable experience. But my name was appearing on the front pages of newspapers, and before long I was getting job offers. And I'm sure if I hadn't had that serendipity, I would never have ended up with a faculty appointment at UBC. Okay, so we jump onto Google Earth and we go out to UBC. And some of you recognize the library and the clock tower, and then the Hennings building. And that's where I started this follow-up project. We'd never seen Cygnus X-3 in a single one-shot sky survey. So how many other highly variable transient sources were there? That was an open question. And we ran this project actually started this project at DRAO. So let me just jump to this next slide here. So phase 0 was at DRAO with a 26-meter telescope from 75 to 76. Russ Taylor did his MSc thesis on this. And Ed Argyle was our very interesting collaborator. We set ourselves a goal which we didn't attain, and that was basically because of the sloppiness of the pointing of the telescope. It would blow about in the wind, and we were doing differential measurements, and so we never could get down to the receiver sensitivity levels. But we did do a survey of a small area. Whoops, let me jump back to that. Got down to a sensitivity of 1 Jansky. But before I could see the writing on the wall here, And so I applied to NRAO and got time to try this out on the NRAO, the Green Bank telescope with a 6 centimeter wavelength, which is a more satisfactory wavelength for doing these things because you want to see into the cores, you need more resolution. So we did phase 1. I had 3 students working on that. Russ did his PhD on that. Robert Braun did an MSc, and Jim Pica did an MSc as well. And that was very productive. That was from 77 to 84. And then finally in 1986, we got a 7-feed system that was put onto the 300-foot. And so Jim Condon and I joined forces. They did the imaging from all these repeats. And I was then responsible for the cataloging and the variability. So I will just jump through. This was some of our successes in phase 1. The most dramatic one was the source here, GT0236 plus 610, which we identified with the luminous stars in the northern hemisphere, 61 degrees 303. And you can see clearly that outburst emerging. We got many more observations and showed that that was periodic with a period of 26 days. That we interpreted to be the orbital period. And so this is the picture that we put together from the optical, from all the wavelengths basically. We believed we had a neutron star which was moving in the dense wind of a rapidly rotating Be star. And we did some really interesting work with that. We managed to use the neutron star as a density probe, and we were able to show that every 4.6 years, the Be star basically ejects a shell, and we could monitor that shell going out using the accretion onto that neutron star. So I want to move on. Here's a bunch of stuff showing that extra period. And that's the density shell moving out. This is the VLBA measurements of the same system showing what they interpreted to be a pulsar. So you can see the orbital phase represented by those blocks. The VLBA resolution is not sufficient to resolve the orbit. It's just a schematic to position the shapes of the images with respect to orbital phase. And it all fit into a very consistent pattern of the theory that we'd been developing. Let me jump to one of our other really remarkable discoveries, and that was a new celestial X-ray source, which had been a blob in an earlier map and speculated it was a supernova remnant. We ended up doing follow-up work, that's Greg Fallman and I, with the Einstein X-ray telescope. And we looked, so this is the image we got of it, and this is the Nature paper in which we published a X-ray pulsar in the center of this. It has gone on to have another life as a magnetar. It's the first of the magnetars, spinning down pulsars that are powered by a decaying magnetic field, a very strong magnetic field. So there's some imaging we did with various telescopes on it. Here's our model for our processing jet model for this supernova remnant and pulsar. And this is the second phase. These are the catalogs we produced from the second phase. And there's some more catalogs you can find on variability from my website. And here's the end of the era. And that's it. I do have a vintage film of the Galactic Radio Patrol. I'm trying to get it onto YouTube. It's only 3.5 minutes. And,
I can help.
yeah.
Are you saying you were using it when it collapsed?
Yes, yes. I mean, I wasn't physically there, but it was my program that was running, yeah.
There's a book called But It Was Fun. I have a copy in my office. Actually, they just sold out their first pressing last week, and they're including that photo of Jack Locke at Green Bank in their next run. and they discussed, there's a whole chapter all about
Yeah.
the day it fell. With,
Yeah.
with the operator. Yeah, so
I could go on for an hour just talking about the demise of the telescope.
I did commissioning work at the GBT for many years, and a couple of years later I found out Greg, the operator, had been observing, and I said, why didn't you ever tell me? We spent dozens, hundreds of hours. And he said, well, Tim, it's not something I like to talk about. We have time for one question, please. All right. I was listening to Gerald's interview, both with you and with Russ Taylor. And fascinating. You should, when we have access to them, you guys should listen to both of them. Russ says at one point when he came out here for that test observation, test year, there weren't accommodations for him, so you bought him or rented him a trailer.
I rushed out and bought him an old trailer, right? And we towed it out here.
We only recently removed it.
Is that right? Yeah.
All right. Well, great. Let's thank Phil again.